data in a nice data table, and that's a nice enough data table. It would make it even nicer if I labeled it with units. So these should be labeled with grams. This should be labeled newtons. These should be labeled newtons. Coefficients of friction don't have a label, okay? So make sure that your nice data table has the units labeled, okay? Your calculated weights, all coefficients of friction, all 20, there they are, right? So there's 10 here. There's going to be 10 more on your other one, right? 2 graphs, one for each surface type. Should have axes labeled, blah, 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 okay? And then part D. You got to write a little thing here, right? Write your own answer to the following questions. Cite data specifically to support any statement you make, okay? How do the static and kinetic friction compare? Cite specific numbers. So I want you to just look at this and just say, in general, the static was more than the kinetic. For example, at 500 grams, it was 2.8 versus 1.8, and on the floor it was something versus something, right? So actually put the numbers in your sentence there, right? 2, come up with a theory as to why they differ if they do. Why is static friction bigger than kinetic? And it's not because objects tend to stay at rest. There's something more going on there, because in either case are we accelerating it. The kinetic friction was measured when it was moving at a constant speed. Static was before it even moved, right? So there's something going on, like they're sticking to the counter, or there's bonds forming or something like that. I've had creative things, right? And then 3 says, the force of friction obviously must depend on the weight more correctly the normal force, but our formula for friction asserts that this is a linear relationship. Does your data suggest a straight line? I want you to look at this data and say, yeah, it suggests a straight line, or no, it doesn't. Talk about it, right? Okay. This data all does suggest a straight line, especially this guy. This one mysteriously has a non-zero y-intercept, and that's because I made it up, and I made up bad data. Your data probably should go right through 0, just like this one's headed for 0. You know what I'm saying? Right? This guy clearly is not headed for 0. It's headed for like a half a Newton. Right? Something with no weight would have a friction force of half a Newton. Figure that out. Yes? Okay? So, it's fairy tale data, right? Okay? But what I want you to do is look at these things and just do some critical thinking. Obviously, if they all line up, that's pretty good evidence that they're linear. These two, even though they don't fall straight in a line, don't suggest anything besides a line, do they? Right? But if your points do this, if your points go bump, 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 that's certainly not a straight line. We can put a line through them. Excel will if you tell it to, but that looks like something else. Looks like a parabola or something, yes? Okay? So when you answer this, basically, write down there, I need you to talk about the linearity of the line. It's a big word, not a big word, right? Talk about the linearity of the line. Yeah? Are we good?
Yes.
Okay. Let us work in this class, let's work in groups of 2 or 3, because I think if we have 4 people, what's that 4th person doing, right? In fact, what's the 3rd person doing? I don't know, right? Okay. So let's work in groups of 2 or 3. You may, if you would like to, okay, you may turn in a common lab report, but if you don't want to do that, you could turn in individual ones. It's up to you. Okay? If you turn in a common lab report, it's my expectation that everybody does something on the actual report. Okay? So somebody might write the answers, somebody might make the graphs, somebody might do the data analysis or something like that. Yeah? Yeah, yeah?